Okay, let's look at example set 1, number 2. So the scenarios is that you drop a physics textbook whose mass is 2 kilograms to a friend who's standing on the ground 10 meters below. Your friend catches it in her outstretched hands, which are 1.5 meters above the ground level. Okay, so what we have here is, you've got this person that is standing and has a physics book and really incredibly long arms. So then down here, and of course this is not drawn to scale, we've got a friend standing here. Drawing people left is always hard. And this person is going to catch the book. And what do we know? So we know that this is 10 meters. I'm just drawing the picture at this point. And I think the outstretched arms are 1.5 meters above. So we'll do this 1.5 meters. There we go, like that. And she's going to catch it. So what's happening here is, we have this object that is way up here, and because you live on the planet Earth, that if that person drops the book, it's going to go from not moving to moving. I mean, you've dropped things before, so the initial velocity will be 0. It's just up there, but it's going to start moving, okay? So the first part of this question is for you to define the system and construct an energy flow chart of the energy transfer during the drop. Okay, what does all that mean? Well, I'm going to back up just a little bit, and if I draw all the forces that are acting on the book once it's released, that would be our gravitational force. And, we're in a magic physics world where there's no air resistance at this point. So we've got our gravitational force. That's it. So what this gravitational force does is it is pulling the object down. So, if you sum the forces in the y direction, there's no force to balance the weight. So the weight force is causing the mass to accelerate. Okay. Now it's going to accelerate, and it's going to accelerate through this change in position here that it goes through. Let's see. There we go. So there's this change in position, and it will be delta y here as it falls down. And it's going to have some sort of non-zero, v is greater than 0 velocity at the moment that it's caught. Okay, so we can look at defining the acceleration in terms of the change in velocity and this change in position. Okay. Okay. So now this is kind of a special case. So don't get too married to our equations here. But if I think back to it, v squared was equal to v initial squared plus 2a delta x. And I know that's a delta x and not a delta y, but it means change in position. Okay, so I can define acceleration as being then v squared minus v initial squared all over 2 delta x. And that will be my acceleration. And, it's totally fine for us to decide that the vertical direction is going to be the x-axis. So, you can grab your eraser there and just decide that, what, we're going to call this, in this case, delta x, and then this will be our, delta x there. Because we don't always move in the x direction. I mean, y direction. So we just kind of coming up with a more general answer here. Okay, all right. So once I have this acceleration defined here, let's look at that in terms of our gravitational force. So the gravitational force would be equal to m times v squared minus v initial squared over 2 delta x. Okay. Now, the amazing thing about the gravitational force is that it's always constant. So I could actually graph the force versus position. And in this case, it's the gravitational force, which is nice and constant, and it's change in position. And remember, I just went ahead and defined it as being x, just so we could have similarities. So this force, this gravitational force, is nice and constant as the book falls through the air. And so, and I've defined this gravitational force and the position here. So the gravitational force and the position there have been mathematically related to each other. And, it's like the gravitational force is as a function of the position, right? That's what I've graphed over here. So, if I take the delta x and I multiply it by both sides, I would have this force, and I'm going to drop the g just so I can be general, like whatever the net force is. It could be the gravitational force, it could be some tension force, it could be a frictional force that's the net force. Just going to be general here. And then times the delta x that's on the bottom, and that would equal m times v squared minus v initial squared divided by 2. And that then, so I have my delta x over here, and then this looks like mv squared divided by 2 minus mv initial squared divided by 2. So what this force does is this net force causes an object to accelerate. That acceleration means that the velocity is changing all while it's moving. And it went from not moving to moving. I mean, in order for a car to go from not moving to moving, it's got to have gas in it. In order for you to go from not moving to moving, you have to have some, eat some food and have some energy, right? And we convert our energy, the foods that we eat, into mechanical forms, like we go and we run. And the chemical energy that is stored in gasoline as the combustion occurs is converted to mechanical energy. And so the car physically begins to move. And we see that as it's like the energy manifests in its velocity. So you may be familiar, probably, if you've had physics before or physical science, that this term right here looks like 1/2 mv squared, which we define as being the kinetic energy. And I'm going to use the notation with a capital E and a lowercase k because energy is the important piece here. Like energy is energy is energy, just like forces are just forces are forces are forces. It's different agents that cause, or interactions that cause the force. And with energy, it's different ways in which that energy is stored in the system. Okay, so this force that's applied through a change in position will cause the velocity to change So the object speeds up or the object could slow down, either, doesn't matter, but there's a change, okay? And so we call that thing that you're doing by applying the force through the change in position, we call that the work. So work is what we are doing when there's a net force applied to an object through the distance. And that force has to be parallel to the change in position. So that work changes the energy. So if I go back over here and look at my graph, then this area under the curve there is the work. That's the work done by this net force that's acting on this object, okay? So we can define work as being equal to the change in kinetic energy. Because if you have this function over here, this is a final kinetic energy. This is an initial velocity, so it would be an initial kinetic energy. And so we get that work causes a change in energy. Now, unit-wise, our force is in newtons. Our change in position is in meters. And saying Newton meter all the time is a mouthful. So we call it a joule for James Prescott Joule, who did lots of studying. His claim to fame was that he was able to connect a mechanical energy change to temperature change. So we call this a joule, J for joule, or that old dude. And so if work is equal to the change in energy, then the unit for energy is also joule. Okay, so because of that equal sign there. So as this book falls, we know that it's going to go from not moving to moving. So it's going to experience a change in this kinetic energy. So where does it get that energy from? What is doing the work to change the energy of the book? Well, that would be the gravitational force. The gravitational force is doing the work there, okay? And so I'm not going to use this word. Sorry. Delete. Okay. So the first part of the question says define the system, and we're going to construct an energy flow chart of the energy transfer during the drop. Okay. So the system is, in my opinion, is the book. So that means that anything that's not the book is not in the system and it's outside my circle. So that would be like the person, or let's see, I think it's you, right? If you read the question. So there's you, and then there is the friend, okay, that's outside of this, not the book. Anything that's not the book. Not the book, the earth is not the book, okay? All of those things are outside the system. So if we want to analyze what's happening, we can create a bar graph. If you remember, maybe in elementary school or something, you may have done a bar graph where you walked around and you asked people, you know, what's your favorite kind of pizza? And you know, cheese, pepperoni, whatever, and you know, you created a bar chart. So we're going to do that same sort of thing as a way to like kind of keep up with our energy and analyze the system. So all these things like you and the earth and the friend are all outside the system. So what I'm going to do is create an axis over here and an axis over there, where this will be the initial conditions, and this will be the final conditions. Okay, so initially, I know that the book is just being held. So the initial velocity is 0, which would make, if I put amount of energy on my vertical axis, and I don't really like the word type, but I can't really come up with a better thing to call it right here. But the type of energy on the horizontal axis. So as far as energy goes, our kinetic energy depends on velocity. And so there's 0 EK to begin with. Let me zoom in a little bit. 0 kinetic energy to begin with. Okay. Now, what is interacting with our book? Well, oh man. Well, the friend is holding it. Put this down here. The friend is holding it. Nope, you are holding it, and the friend's going to catch it. So while it's in the air, you are not interacting with it. So there's no interaction between you and the book while it's in the air. There's no interaction between you and the friend while it's in the air. Okay, but the thing is, the earth is interacting with the book. Okay, later we know that it's definitely moving right before the friend catches it. And so I'm going to just randomly choose 3 blocks here for the amount of energy that the kinetic energy the book has. It's just a representation. Okay, so the earth though is acting on our book. It does something to it. It's doing work. There's work done by this gravitational force because the gravitational force is parallel to the change in position. Okay, and I'm going to use a Y there. So the gravitational force is doing work on the book. So I'm going to draw some blocks going into the book system. And if I have 0 blocks here and 3 blocks over there after the interaction with the earth, then this must be also 3 blocks of energy is inserted. We're going to do some work on the system, and work changes the energy. So this work done by the gravitational force is equal to our change in energy. So the next part is using the energy bar chart, create an energy transfer equation and determine. Okay, so I used the book as its own system. Okay, well, what if the earth and the book are in the system together? So if you have the book plus the earth in the system together, okay? Now, in terms of the work done by the gravitational force will be negative mg times final minus initial. So negative mgy minus mgy initial. So this work done by the gravitational force is equal to this change in, well, work causes a change in energy. So this must be a change in energy. And this is an energy that is very specific, that the mass has to be in a gravitational field. So, and not its own gravitational field, because the mass doesn't apply a force to itself. You can't pick yourself up. So this means that I have to have two bodies interacting. So this mgy, the m represents the book and the g represents the gravitational field due to the Earth. And so when they're in a system together, they can have this energy stored, and we call it the gravitational energy. Mgy is the gravitational. Okay, so if I've now moved the Earth inside the system with the book, initially the book is above the ground, and so the amount of energy in terms of gravitational energy is maybe the I can represent that with a 3 blocks. So this is initial, and then this will be final over here. And initially, it wasn't moving, so this is EK initial, no, 0. And then later, when right before we catch it, it's reached where we're going to call Y equals 0. And so if our gravitational energy is mgy and Y is 0, then your gravitational energy is 0. And so this will be EG final is 0. And then because energy cannot be created or destroyed, only transferred, and work does the transferring. It's the agent that does the transferring, but there's nothing outside my system in this case. I would get 3 blocks these 3 blocks of gravitational energy are now the kinetic energy. And so then I can write an energy transfer equation. So I have EG initial, EK naught is 0, so I'm not going to include it in my equation, is equal to EK final. Okay, so part B is asking us to find the is asking us to find the initial and final gravitational energies of the book just before you release it. Okay, so the EG initial will be mgy as derived up here. The mass of our book is 2, G is 10, and then Y is initial. And let's go back and say that we start at Y is equal to 10, Y naught is equal to 10 meters, and our final position is where the person catches it, our friend catches it at 1.5 meters. So we have just a little bit of energy left here in the gravitational field. So we'll add that over here. There we go. The fact that I gave an initial position and a final position that was non-zero. So we get 200, and remember energy is work, and work is Newton times meter, so energy is also in joules. And then, let's see, the other question was what is the final gravitational energy? And so the final gravitational energy would be mgy, so 2 times 10 times 1.5, and that will give us 30 joules. That equals 30 joules. All right. So now in BII, we want to determine its kinetic energy just before your friend catches it in her outstretched hands, which are 1.5 meters above the ground. So we created an energy transfer equation that EG initial will go to EK plus EG. We calculated this initial gravitational energy to be 200. The EK is what I'm looking for. Our final gravitational energy was 30. And so then our kinetic energy would be whatever 200 minus 30 is, which is 170. Again, joules is the unit for the energy. And then the next piece was just to find the speed of the book right before it's caught. So I'm going to go do a B triple I over here. And if the kinetic energy is 1/2 mv squared, then 170 would equal 1/2 of 2 times v squared. Remember the mass was 2 kilograms. And so I take the square root of 170. And remember, you get plus or minus when you take the square root of something. And in this case, if I'm looking for the velocity, it would be negative 13.03. If I'm looking for the speed, you would just report the number, the 13.03 meters per second. And that is all of question number 2.